Hello and welcome to today's seminar on compensating for springback. My name is Derek Barkey and I work in Saratech's Consulting Services Group. Today we're going to introduce the process of springback prediction, illustrate how to set up the model, and then we're going to perform a demonstration. So what is springback? Metal forming strains the metal so it takes on a new shape. You're stretching it plastically. Elastic recovery causes some of that strain to be lost once it's unloaded, which is the elastic strain increment you see in the diagram at the right. In order to compensate for this loss of strain when the load is removed, you must actually overstrain the part so it has the correct shape after that elastic recovery. You can minimize springback by reducing yield stress, for example, using material with a lower yield stress, or heating it or using a material that displays superplasticity, or forming it in the annealed condition. But regardless, you're always going to have some degree of elastic springback. In order to compensate for this, we need to be able to predict it. And in order to predict it, we need to do a nonlinear finite element analysis, because this process involves contact, plasticity, and some processes display large strain and creep, all of which require a nonlinear finite element analysis to capture. Fortunately, Nastran has a powerful nonlinear analysis capability. There are actually three different options you can use inside Nastran. There's the legacy solution 106, which could do this in theory, but since it doesn't have surface contact, it would be kind of cumbersome to use. You'd have to do it with gap elements. It's possible, but probably not very easy. Better alternatives are either the advanced nonlinear capability, also known as solution 601 and 701, and 601 is what we're going to illustrate here, or to use the newer multi-step or kinematic nonlinear solution sequences 401 and 402. This is the algorithm we're going to follow. So we're going to start out by creating a finite element model of a blank and a die. We're going to apply the load and then we're going to unload it. Once it's unloaded, we'll see what its shape is after springback. And we'll determine what the error is over our desired shape by subtracting the deflected shape from the desired shape. Then we'll decide whether that error is acceptable. If it is, we're done. If it's not, we'll adjust the shape of the forming die by subtracting that error from it. Create a new die FEM and repeat the process. So the demo model for today is a representative aircraft part. It's 063 thick 2024 aluminum, and we're going to use a forming process called hydroforming, where the part is pressed against a tool using pressure. You can use the same basic approach for virtually any metal forming process, whether it be hydroforming like this or stamping. Stamping would look pretty much the same, except you'd have two different forming dies rather than one. Superplastic forming would look very similar as well, except in that case you'd have a superplastic material model that you'd have to allow for, and you'd have very large strains. But the basic process looks the same in terms of setting up the contact and performing the simulation and doing the compensation. So here's the nonlinear properties we're using for our model. Now a note about using nonlinear materials in Nastran. Stress and strain can be defined in two ways. There's what we call engineering stress and strain, which is what most of us use and what most stress strain curves are defined in terms of, which is simply load divided by area. But of course, once we start applying the load, the area changes. So there's also true stress and true strain, which are the actual stress and strain that allow for the fact that the material shape is changing as you pull on it. The advanced Nastran or advanced nonlinear Nastran solution sequences 601 and 701 expect to see their stress strains defined in terms of true stress and true strain, not in terms of the engineering stress and strain we're used to thinking of. So in this case, I've defined it in terms of engineering stress and strain. there's an option which I'll show you later on in Nastran which will automatically convert that for you so that the solver actually sees the true stress and true strain. So here's the model we're going to use. So I start off with a flattened blank. So this is what the part looks like before it's formed. And I've meshed that with a relatively fine mesh, and I've positioned it just above a meshed surface that represents the die. Now, for this first iteration, the shape of the die is the desired shape. But of course, we know that once we release the load and we get spring back, we're not actually going to get that desired shape. We'll have to adjust this die shape as we go. But for the first iteration, it's the actual shape we want. I have it positioned just above this die surface. And the contact algorithm in NX Nastran is smart enough to compensate or understand that even though I've meshed this with shell elements, they actually have a physical thickness. So I have to position the blank above the die mesh, not exactly above it, but I also have to have half the thickness included in that gap so that they're not actually interfering with each other. These are relatively fine meshes. These are relatively small models, so you might as well use a fine mesh, and the fine mesh also lets us get a nice, relatively smooth surface that's not very faceted. The tool surface is going to be represented as being rigid, so its thickness is really kind of irrelevant, so I went ahead and made it relatively thin because I don't want Nastran to get confused by a thickness associated with it. And then I'm going to define a pressure load on the blank that will push it down onto the surface. In order to keep track of all this, I'm going to create a local coordinate system so I can define constraints in that local coordinate system. And I'm going to assign all these nodes to have their displacement coordinate system be in that local coordinate system. So you can see the local coordinate system number 3 in the image at the right. Its x-axis is aligned with one edge, and the y-axis is basically aligned with the other edge, and the z-axis is basically normal to the surface at this point. I'm going to create some in-plane constraints, which is those triangles that you see, to hold it in the xy plane of this coordinate system. So I don't want my blank to be moving around while I'm trying to form it, and so that will hold it in place. I won't constrain it in the normal direction though, because I want it to be free to move up and down as I apply pressure. I do, however, want to constrain all 6 degrees of freedom of the tool surface. Obviously, I don't want it to move, I want it to be rigid. Now with a rigid surface, you actually assign it to a master node. And that node has all the degrees of freedom of that rigid surface associated with it. Essentially what Nastran does internally is it creates a rigid element in RBE2 that connects that master node out to all the nodes on the rigid surface. So the actual constraints for the rigid surface go on that master node, and I'll demonstrate that later. And then of course we're going to define contact between the tool and the blank. Now I've constrained it in plane with those constraints I showed you. And in reality, vertically, it's effectively constrained by the contact. If I put a load on it, it's going to collide with the die, which of course is the objective of the contact, and that will keep it from moving vertically. But in order to be able to make a comparison from one iteration to the next, it's really convenient for me to have the part go back to essentially the same starting point each time, so I can see exactly what's happening from a forming standpoint rather than just looking at, say, a effectively rigid body motion of the blank. So I've put 3 very weak springs here that should lift the blank back to at least those 3 points back to their starting point. And that way I'll get a consistent, comparable reference position with each iteration. I make these soft enough so that they don't actually interfere with the forming itself. You don't really need a really big spring stiffness here just to move it back into position when the load is removed. Let's talk a little bit about setting up the nonlinear analysis now. So there are a few things we're going to do. We're going to turn on the auto increment. What this does is it lets Nastran adjust the load increment size. So if it's having problems converging, it will divide the load step into smaller steps in order to converge more reliably. We're going to call this a low-speed dynamic analysis with a damping factor. What that does is Nastran treats this basically as being kind of a quasi-dynamic analysis. And when we apply the load, the part is going to have slower movement than it would otherwise, because it's going to, this damping factor is essentially going to treat it almost like it's submerged in pancake syrup. It's going to, as you push down on it, if it tries to move too rapidly, this damping will slow it down. So that will prevent us from having, say, an initial deformation that's hundreds or thousands of inches. Instead, it will restrict how much load or how much displacement you'll get on each load step. Now, as the part starts to reach an equilibrium and its motion diminishes, then this damping force will also diminish. So it should go to zero effectively once the part is firmly against the die, and it should effectively go to zero once the part has sprung back and reached an equilibrium shape and stopped moving. But in between, this damping force will help stabilize the part. We're also going to turn on damping for the contact, which causes the contact to behave a bit more stably. Also, don't forget that option to convert stress and strain, and I'll show you that later in FEMAP. So here are the results. The part deflects until it's held against the tool, and once we release it, we get some spring back. That deflected shape, when it's held against the tool, since we're actually holding it against the tool and the tool is the desired shape, we're going to call that shape the desired shape, and we're going to define it as being UD. And we're going to say our current tool shape is UI. Now in this case, UI and UD are the same for the first iteration. But later on, as we start to adjust the tool shape, UI will vary. We're going to save this UD for reference, though, because it now becomes our desired shape for all of our iterations, and subtracting it from the sprung back shape is how we'll define our error. Okay, so the sprung back shape we're going to call UF. So if we actually looked at the full solution sequence, this is kind of what it looks like. At the start, we have our nice flat blank positioned over our die. At full pressure, you can see it's being pressed tightly against the die. And then once we release that pressure, you can see how at the corners it has sprung back. Something to note about the pressure I'm applying here is your forming process may have a fairly high pressure. I don't think you need to feel constrained to actually use the actual forming pressure. You just need enough pressure that it actually deflects the part and holds it against the die. Any pressure above that's really not having any significant effect on the part. And using a really high pressure might move the part relatively violently in the simulation and cause it to have trouble converging. So you may find it's helpful to adjust the pressure you're applying so it's enough to press the part against the die, but not so large that it causes a really violent response from your model that causes convergence problems. So let's talk about how we go about calculating this error. As I mentioned before, we're going to call the sprung back shape after the load is removed UF. And the desired shape is this initial iteration when the part is pressed against the tool, which we call UD. So we can subtract one from the other in FEMAP by going to the Model menu and looking for the Process Output feature. And when you do that, you'll see there are several options for processing output, one of which is linear combination. So what this lets us do is it lets us add the displacements of UF with a factor of -1 on them to the displacements of UD. Effectively, we're subtracting UF from UD. And that's what you see illustrated on the right. And when we do that, we get a new set of results, which we can then plot. And here's those results. So you can see there's a bit of an error. At one corner, it's -0.1339, and then at another edge, it's -0.02. If you were to look at the difference between those, then effectively we've got an error of about 0.11 inches, which is pretty significant when you consider our part's only 0.063 thick. So we need to adjust our tool shape, our die shape, to compensate for this. So the new tool shape, which we're going to call UI plus 1, is the current tool shape UI minus the error UE. Well, since the error is in reality UF minus UD, we can actually combine those into one equation. So the new tool shape is the old tool shape minus the sprung back shape plus the desired shape. And again, we can do this calculation using the model process output option in FEMAP. Once you do that, you'll have a set of results that represents what the new tool shape should be. Now we need to create a surface of that so we can mesh that and use that as our new die shape. Well, since I don't really want to go back in and change my model permanently, I just need to generate a new surface. I'm going to create a copy of my database. I'm going to open that copy. And what I need to do is I need to take the nodes of the blank and move them to this new tool shape. Then I'm going to create a surface from that, and then I'm going to export that surface and use that as my new tool surface. So in order to move the nodes of the blank to this new tool position, this new tool shape, there's a feature inside FEMAP to move the nodes for me. And that's actually not a core FEMAP function, it's actually an API function. So if you're not familiar with the API functions, these are Visual Basic functions, typically Visual Basic, that are provided both as utilities to FEMAP users and also as illustrations of how you can write your own APIs. So you can actually see the source code for these. So if you look under the custom tools, under the post-processing sub option, and look all the way down, you'll see there's something called move nodes by deform. And that's what we're going to use in this case. We're going to use that function to take our blank and move it to the new desired tool shape that we've calculated. Once we've done that, then we're going to convert that into a new surface using an option under the geometry menu for surface from mesh. Once we've got that new die surface from this moved mesh, we can basically throw this database away. We're going to export this surface, throw the database away, read that surface back into our original model, and replace the die shape we had in the original model with this new die shape. And we're going to repeat this analysis until we get a good part. So here's our error from our second iteration. So we went and we ran it with this new surface as the die, using the exact same blank model. And we find that we get an error of about 0.02 inches. So we went from about 0.011 down to 0.02. Well, this is less than a third of the thickness of our plate. So I'm going to consider this adequate in terms of error. If you decided you needed something even better than that, then you could run through as many iterations as required to get down to the error that you were looking for. But I think this is probably acceptable, so I now have a compensated die shape. So at this point, I'm going to try and demonstrate some of these features in FEMAP. So here's the model in FEMAP. So a few things to note. Let's talk about the rigid surface first. So this is my rigid surface. And it has a rigid property associated with it. So you can see it's defined as type, it's a contact, and it's a rigid surface. And when it's a rigid surface, some of these other parameters are turned on. If we made it glued, some of them would be turned off. In this case, it's just a simple contact, so everything's turned on. If we look at the actual surface definition itself, recall that I said that all of the nodes of a rigid surface get tied back to a single reference node. In this case, that's the reference node, node number 1. So all of my constraints for the rigid surface go on node number 1. One thing to note that I don't think is described in the documentation is that node number 1 has to be a node by itself. It cannot be part of the rigid surface. It has to be basically a standalone node. If I was doing a forming operation like, say, stretch forming, and I actually wanted to move the tool, then I would define that movement or that force on the reference node instead. See a couple of other things I mentioned. The post-processing function to move nodes by deform. This is where you'll find that. And I also described the process output. Which can be found here. So I want to do a linear combination. I want to subtract my final, which in this case is at time 2. My desired, which in this case is at time 1.05. So if I do that, and look at my results, you'll see I have a new set of results here that represent that error, which I can then post-process. And there's my error. We discussed analysis setup. Which you'll find here. Here's that option I mentioned to convert your stress strain into true stress strain. So you need to check this box if you're using engineering stress strain. And this is where I turn on auto increment, define my damping, and also turned on damping for contact. So that was my demonstration. So in summary, nonlinear analysis allows you to predict and compensate for springback. Using functions in FEMAP for combining results, moving nodes to deform shapes, and creating surfaces from mesh, you can create surfaces for forming that are compensated for the springback. That's all I have for today. Thank you for attending. Please follow us on Twitter, Facebook, LinkedIn, YouTube, and our blog on our website at saratech.com. Have a great day.